I have a Discord channel, so if you need any questions regarding VScript or anything else, check out this channel. It'll be in the description, and I'll try to be here to help you with your VScript, Hammer, or anything else that you need help with. Welcome to today's video. Today is mostly theory side, and can work with other languages. So this would be how to make better programming, which can make your Squirrel code more faster. Let's begin. The goal of optimizations is to achieve the same result, but with fewer restrictions or yield a result in the less costly way possible. Most programs and IDEs already have an optimizer, especially compilers. Typically, if you worked with programs, at the end of the build, you will compile it as a release, as it will contain less bloat that comes along with debug releases. Debug release is higher and more costly in instructions as it does not change the instruction set and contains extra information to allow us to breakpoint if need be. In terms of using it in Squirrel, you don't have this luxury as you're mostly working with an interpreter instead. This is good for map testing because all we have to do is save the script and read on the map and the changes are right there. But the problem is once you finish that, we still have to go through line by line, which is very bad. But Squirrel cannot do any of optimizations at all because it doesn't know how to, and it's too costly to run and even evaluate if so. So we have to have good scripting practice, which will make our script run faster and more efficient. You can use these techniques in other programming languages too, so you're doing an extra bonus for watching this video. The first one is dead code elimination. Dead code can be evaluated with the current rules. If the code is never used, or a certain variable or logic is never reached, or if the variable only has been ever written to and not read from. This will prevent variables to be created without any long-term need, prevent unwanted instructions from being predicted, misprediction, like branches, if statement, switches and all that. The code is very useful in cache and memory, and it'll make the logic less bloated. The first example. Let's evaluate this logic, and let's go step by step and to see how we can make it better using dead code elimination. We can't evaluate yet, but line 1 is fine as it is. Same again with line 2, no changes. And yet again, we can't evaluate because it's too early yet. We now reach the first conditional. This means the chance of hitting this is most likely, assuming that we're only working with constants. If we're not working with constants, this may slightly change, but not likely, depending on what the result will be. Although this is not optimized, we've hit a true case. We assume this as the numbers will not change, but at this point, we've hit a return, which means this is the end of the script, which leaves the last lines as redundant because those will never be reached, assuming that we're working with constants. If we're not working with constants, the chances of this being hit is more likely, but in this case, as we're working with constants, numbers that won't change, this code here will never be executed. Yet again, this is non-eliminated. And here's the script, shrunk by using dead code elimination. The first stage is to turn any expression into a variable. We want to cache the result to prevent more calculations of the same number being generated. So in this example, line 4 holds the expression, and then we reuse this expression as the last one done those calculations twice, even though it shouldn't have. We now do constant folding to the constants, which means we have less variables compared to the last one. Here we see we have 1 and 2, which contains numbers equally. We can eliminate that by just simply giving the instructions as constants instead of 2 separate variables. We can yet again do constant folding, assuming that we're working with constants again, and we can prevent multiplication by giving the answer right away. So instead of doing this multiplication, we already have the result here, which is faster. And if you're a compiler, we just simply return 30. But we're not likely going to hit this with Squirrel. Caching is the ability to store data in the register and CPU. But depending on its architecture, its L1, L2, L3 can vary, but is always lower than RAM. We cache variables or results that we want to gain faster access to, but we have to be careful as we operate in such a low storage store. We can fix this by doing common issues that we do on a daily basis. The first one is bloating up with unnecessary variables. Here's your 2 loops. What one is better? Let's evaluate the first one first. Here we have 3 variables, count, I, and add number. But if you look at the code, these variables in the scope do not add up. Let's actually see what it's actually like. Because we use local, that means we always have to construct the variable each time it's called. Now this is an issue because we only needed 3 variables and now we got probably 8 or 7. This is all because we construct a variable by using local. The solution is to create this outside the loop and only assign it to it. As we see here, we only have one variable and we always assign it. It's much faster and we don't always need to create the same variable. All we have to do is reassign to a variable that's already there. And that's the simplicity of caching. A branch is a decision made based on an instruction, commonly a jump instruction. These include if, while, for, until, and switch, and many others depending on what you use. These can be costly, especially if the branch predictor gets it wrong. We can prevent this by doing basic optimizations. We have to assume that we're getting a yield a result here. Let's validate if something is true or false. A range or condition is required. You may consider using an if statement if you're brand new to programming, but there is a more simpler and more cost-effective approach that we can use instead. If you use the information from the last page, you should be alerted that something's wrong here. Let's go over it. Here, we only have one if statement, because if this is not true, it's already assigned false. So there's no point having an else statement if it's already been assigned false. If we look at the last slide, notice here we have false. There's no point for an else statement as it already is the value that it already is. But we need to look closely at machine language. The closest we can do this is assembly. But let's simplify how it works. These simple 3 lines will be typically generated into assembly language or an upper language that's written to the far right side here. But this is simplified because not everyone knows how instructions work unless you spend time into it. Each virtual machine has a scope, which uses a data structure called a stack. It acts like a list, but it performs differently. The assembly first grabs what variables are needed to run the instructions. All these variable types are primitive, so they'll be stored into the CPU cache. The first 2 elements are what we defined. We know this because it has a name assigned to it. The second and the third element has no name, so this is anonymous. This will be the result from the S statement and the constant of 18, which will be the validation for the boolean. So now we've got the variables that we need into the local scope, but we have to assign them to what we wrote. So now let's do that. We do this by loading and storing the information into the stack at the first element by pushing it. Then we have to pop the element out into the corresponding local scope to the variable that we need it to be. So this will typically be an index. So for the next example, we load false to the stack as the first element, then we pop the element or we store the element into the local index 0, which would be can drive boolean. Now we load 20 into the stack, or we push it to the stack, then we yet again store or pop out the element from that stack into the first index of the local scope, which would be the age or the input. Now let's evaluate this step by step with a visual stack and a visual scope. Here we see false being pushed into the stack. We then pop out that element from the stack into the first element or the 0th element, which would be can drive. Pay attention to the index here, 0, 0, and that is can drive. And that would be evaluated false based on the stack. Next, we load 20 into the stack. And again, we pop out this element from the stack into the local element of 1, which is age, as we'd expect it to be. Now let's compare it. For comparisons, we usually need 2 variables in the stack for it to be compared. So let's do that. The first thing we load is the age. Then next, we have to pop in the validation, or the right-hand operand, which is 18. If you remember the last snippet, this is going to be the if 20 is more than 18 validation, or if age is more than 18. That's what the next instruction does. The next instruction pops those two out and does a comparison and loads it into the stack. Notice that the compare more than took the two values from the stack, popped both of them out, and yielded in a true. So it pushed in a true result from the two variables. Then we tell it to compare it into the local element of 2, which is the third element. Notice the arrow, it popped it into the second, or in this case, third element of the local scope. But then we have to pop that back out because we still need to validate the if statement. So now we have the boolean done for us. Now, here comes the hard, tricky part. Now, since we have the result from the if statement, we now need to do a branch validation. Typically, branches are always evaluated to false, and if it's not reached, it will continue onwards. Now, the branch would take false into consideration. If the result is false, we jump into the L1 instruction. But in this case, if you look back, notice is the stack has a value of true. So this will evaluate false. But if this was false, we will jump into L1. But in this case, we haven't gone false. And since it's true, we jump into return of 1. And notice that this is the validation of 20 more than 18. And once we hit return, that's us done for that part. Now we can improve this greatly by using a ternary operator, or we can just use this expression which will evaluate true or false. The problem of if statements is if. A Boolean expression or ternary condition is not questioning, but returning a result or a definite answer. Jump instructions can be unpredictable, remember that, as conditionals are straight to the point. So if you use branching, it's more costly because you have to do if or false, and these typically can get complex the more if statements or switch statements or for loops you commit. But an expression or a ternary condition only has to give back a result. There's no jumping and there's no much validation apart from the condition it's given. So if you can, use a ternary operator or expression which evaluates true or false over an if statement, but sometimes you can avoid it. Now for lookup over switches. The reason we cache is to reuse previous calculations or results to prevent the program to use those extra instructions again. Compilers are fantastic for this. But let's assume that we have an animal that we type. And depending on what we type, it responds back with a different response based on what I put in. The one from the left is using a switch statement, and the one from the right is using the table, or in most cases called a map or a dictionary. But you might consider why use a map, a dictionary, or a table in Squirrel's case over a switch. It's faster. We avoid doing any jumps, but we lose the chance of validation if the input does not exist in the table. Because the switch case has a default case which jumps if nothing happens from the validation given in. And the other reason why it's good is because it's cached, because we don't need to recreate the same strings or values over again. It's faster to read than it is to recreate a new string or value. This is true. It's always faster to read than it is to create. Now let's look at this code. Can you see the fault? We keep using the length function, and if this function does not change in size, if it shrinks or doesn't shrink, this is an unnecessary calculation that we do each time, or a fetch that we don't need. We can solve this issue by caching it into a variable called size, which contains its length before going into the for loop. This is now faster because there's no need to fetch the different size. So always try and use a variable for size for validations for while loops or for loops, if possible. So that's the end of the video.